gradient descent is a fundamental method in training a deep learning network. It aims to minimize the loss function by updating the model parameters in the direction that reduces the loss. By using only batch of the data, we can compute the direction of the steepest descent. However, for large networks or more complicated challenges, this algorithm might not be successful. Let's find out why this happens and how we can fix this. In the previous video, we already developed the deep learning network, and here is our framework. We have parameter initialization function, linear layer, we have binary cross entropy loss, sigmoid function, leaky ReLU activation that we use as the activation function between layers, and the sequential module that help us to compose our layers. Also, we have this spiral dataset function that create for us the spiral pattern. And let's run this code just to initialize our training framework. Also, we have this code that generate the synthetic classification data. It looks like this. We have a spiral dataset with two intervening spiral, red one and blue one. So basically it's just two classes, red and blue. And the goal of our training algorithm is to split red one from the blue. Here is our demo momentum stochastic gradient descent optimizer. We prepared this code in the previous video, and that's basically our training loop. So you can check how we built all of this in the previous video. Today I want to show you the fundamental problem that happen when we run our training loop, for example with the learning rate 0.01. Let's rerun the code. So this learning rate just causes the optimizer to bounce around some local minima. Even with lower learning rate that we used before 0.001, this problem can occur sometimes. When the optimizer moves too far in steep areas of the loss surface, the update bounces back and forth. And you can see it right over here, our training just unstable, and we have an overflow in exponential method right over here, when we call sigmoid function, it's just it's just an overflow, And today I want to fix our stochastic gradient descent and make it work much more stable with quite simple fix. In this chapter, I used the training loop code many times, and let's build a unified training loop creator. Let's drop this code. Let's create a function training, or train, whatever. So we have a model as the parameter, loss function, optimizer, and number of epochs. So let's just reuse this code, and we can use this number epochs right over here. Instead of the binary cross entropy, we need to call the loss function in forward mode and then in the backward mode. And I think that for the optimizer it looks nice. So everything should work as we expected. Now we have this training function that basically rerun our model and print for us an information about the epochs and the loss results. Let's just rename this function to train model. I like this name, train model. So let's run this code. We create this function, and now we are ready to run our training. Let's, for example, just retrain our model with binary cross entropy, optimizer, stochastic gradient descent, and learning rate 0.01 for 100 epoch. And I can see that we can reproduce this fail of our stochastic gradient descent optimizer. In my previous video, I used separate terms for the momentum and the gradient direction. You can see this mu term for the momentum and the alpha term for the gradient inside the stochastic gradient descent. But it's just for demonstration purpose. This is not the standard way of applying momentum. Yeah, we then apply this momentum. Yeah, the update rule of our position looks like this. We compute the next step based on the previous plus this momentum, or let's say momentum quote term. Yeah. So, and the update rule for the position becomes like this. We compute the next coordinate based on the previous plus this velocity term. And it looks like this in the code. Yeah, we multiply the momentum term times this velocity minus the learning rate times the gradient and update parameters just at this computed velocity step. Now let's use the standard momentum, where we have this mu term that controls the influence of the previous gradient. We multiply mu times the velocity step plus 1 minus mu times the gradient of the current position. And the update rule for our position, where alpha is the step size, looks like this. We subtract from the current position our alpha times the velocity term that we compute on this step. And this is the correct implementation. We use both terms in the negative direction, the velocity and the gradient. Okay, and let's fix our stochastic gradient descent momentum implementation. We have this first term, self momentum times the self velocity. Yeah, it's exactly first term from our formula. Yeah, for the velocity term. And for the second term, we need to add 1 minus the momentum times the gradient. And I think that this is exactly what we need. We multiply the mu times the velocity and add 1 minus mu times the gradient. Yeah. And as the second step, we need to update our coordinate. We need to subtract from the current coordinate the learning rate times the velocity step. And we need to subtract self dot the learning rate times the self velocity parameter ID. I think that this is exactly our implementation of this update rule. And now let's rerun our code, and we need to copy our model. We just recreate the model, binary cross entropy, and our optimizer. Yeah. As far as I remember, previous time we just failed to converge. Yeah. Right now let's run it again. And you can see that right now we have no any errors. Yeah, our algorithm works fine. We have stable movements toward the global minima, but I think that we have not enough epoch. Let's increase the size of the epoch to 500 and rerun this code again. Okay, and after we rerun this code again, you can see the result. Yeah, we have almost perfect loss for our model. And we can visualize our decision boundaries with this method plot decision boundaries. Yeah, we put model, our x and y target. The stochastic gradient descent optimization algorithm with vanilla momentum works stable, and it's almost perfect. The spiral pattern is highly non-linear, which makes stochastic gradient descent struggles. You can see that right now we have 500 steps towards the global minima, yeah, towards the solution. Momentum helps speed up convergence in consistent direction, but it can amplify the problem too. Momentum accumulates large changing gradients, and the velocity term can become too large, and large gradient updates cause oscillations. And it looks like this, yeah. Remember, here we have this momentum term, yeah. We multiply mu times the previous momentum plus 1 minus mu times the gradient direction at the current step. Then we update our step, we subtract the alpha term times the velocity. And we can write it in full mode like this, yeah? And then let's use our alpha, for example, 0.1 and mu 0.9. If gradients, this nabla f of xt, are large, which is common in deep neural network, the velocity term can build up, yeah? We just sum up this gradient step with the previous gradients accumulation, with this velocity term. And this causes stochastic gradient descent to false, yeah? We just overflow some function and starting to bouncing around some local minima. And right now we use a quite small learning rate. Let's try to use, for example, 0.1, yeah, as in our formula. Let's recreate the model, binary cross entropy and optimizer with the new parameters and rerun our training loop. And it looks like this, yeah, same trouble. We very fast started to false in some local minima and no any convergence, no any movements towards the global minima, towards the solution of our spiral pattern. You might proudly tell me the learning rate is simply too high. Reduce the learning rate and the result will stabilize. But I know the better way to fix this, and this fix will work even with the learning rate 0.1. To fix the exploding gradient problem, I use the gradient clipping. It limits the size of the gradient to a min-max range, and it ensures that the gradient won't explode during backpropagation. Let's right now implement this logic. We need to copy our stochastic gradient descent code and let's paste it here. Okay, let's add one more term. We can call it a clip value. Let's use the float by default and install, for example, 1.0. Now we need to add this to the class property as the clip value. And now, before this step with the momentum update, let's just use the gradient clipping. Okay, good. If self.clipped value, let's say more than 0, we can call numpy.clip. We use the gradient variable, and then we need to use minimum and maximum. Okay, let's use negative self.clip value as the minimum, and as the maximum self.clip value. And we need to define the out variable. Let's use the gradient as the out. Yeah, we just override the gradient variable. Okay, now let's reneat the stochastic gradient descent. We can copy our training code and let's paste it under the stochastic gradient descent. We use the learning rate 0.1, yeah. Let's run for 100 epoch and run this code. And you can see the result, yeah. Right now, for 100 epoch, we have almost perfect score. And we have almost stable movements towards the solution, yeah. We prevent this bouncing. We have small troubles, yeah, like this one, yeah, between 0.58, 0.59, yeah, but then it converges very fine. And let's also plot the decision boundaries, yeah, just to check our result of the training. It's almost perfect, yeah. And also we reduced the training epoch by more than like 5 times, yeah, because we use only 100 steps, yeah, only 100 epoch. and we got approximately the same result as before. Yeah, with these two simple fix, yeah, with the vanilla momentum and with the clipping of the gradient, we right now have very stable stochastic gradient descent implementation, and we can use this for a little bit more advanced datasets.